The CMS collaboration at the LHC at CERN in Switzerland reported a possible family of particles that may be composed of 4 heavy charm quarks at the 41st International Conference of High Energy Physics in Italy on July 9, 2022. The paper has been submitted to Physical Review Letters on June 12, 2023. The potential family of particles was observed decaying into a pair of particles called J-psies using proton-proton collision data collected from 2016 to 2018. Normally, a particle is composed of 2 or 3 quarks, and most commonly, they consist of light quarks. However, a state composed of 4 of the same kind of heavy quark is very rare. A family of them is even rarer. And even more interesting, these 3 states may get entangled, be enhanced or diminished due to an effect called interference. According to our investigation, the 3 states are reduced. The 3 states are tentatively named X6600, X6900, and X7300 based on their masses. The first 2 are observed at a near statistical certainty, while the evidence for the third one is not quite as strong. The existence of X6600 and X7300 was seen for the first time by CMS, while X6900 was previously observed by the LHCb collaboration in 2020. The CMS collaboration provided a confirmation of X6900. Well, you may have a lot of questions in mind. For example, what is a quark and what is a heavy quark such as a charm quark? What is a J-psi particle? What are the X6600, X6900, and X7300? Let's start with the composition of matter. Even in the ancient world, thinkers speculated about the nature of matter. For example, the ancient Greeks proposed a 4-element theory, including water, fire, earth, and air, while in ancient China, there was a 5-element theory, with gold, wood, water, fire, and earth included. But it was not until recent centuries that scientific theories, that is, evidence-based hypotheses, were put forth. Beginning in 1803 and stretching into the early 20th century, the modern atomic theory was developed after successive studies by John Dalton, Joseph Thomson, Ernest Rutherford, and many other scientists.
Although atoms were proposed as the ultimate constituents of matter, the 20th century saw new and deeper layers of structure exposed, culminating in our current understanding that all the matter we know in daily life is composed of electrons and quarks. Murray Gell-Mann and George Wegg proposed the quark model in 1964. There are 6 types of fundamental particles called quarks in this model. The up and down quarks along with electrons are the building blocks of our world. Each type of quark has its own antiquark. Among them, charm bottom and top quark are called heavy quarks because of their distinctively large masses. Well, due to its enormous mass, the top quark decays so fast that one cannot actually build other particles out of it. It is the heaviest known particle, almost as heavy as the atom of tungsten. The other quarks can make a vast array of hadrons, but they are, aside from the protons, unstable and in time decay away. We learned most of what we know about quark binding by studying these particles, even though they have only a fleeting existence. The conventional types of hadrons in the quark model include mesons and baryons. For example, the J-psi meson is composed of a charm quark and anti-charm quark. States consisting of 4, 5, or even more quarks are called exotics. For instance, X6600, X6900, or X7300 are possibly composed of 2 charm-anti-charm pairs, that is an all-charm tetraquark state. Their mass values are consistent with some theoretical predictions for a family of radio-excited states.
The first heavy exotic meson, named as X3872, was discovered in 2003 by the Bell experiment. It set off an intense wave of interest in exotic hadrons and became a hot topic in our field for the last 20 years. However, all prior exotic hadrons include both heavy and light quarks. until the observation of X6900 in 2020. As noted before, the 3 states reported by CMS may be a family of radio-excited states. Think of each heavier state as having a larger quark orbit. If so, this provides us a new window to study the strong interactions that bind quarks together. The physics of all heavy quark states is simpler to model, since heavy quarks are not moving near the speed of light, and thus they offer a clarity difficult to achieve with other states. This family of exotics is most obviously thought of as TETRA-CHARM-QUARK states, but other novel possibilities exist: hybrid states, molecular states, and even as a kind of kinematic effect. For now, the true nature of these states is a mystery, but whichever possibility proves to be true, studying all heavy exotics promises important advances in our understanding. The LHC is currently collecting more data, and CMS is preparing to measure more properties of these states, including such as their spin parity, cross-section, etc. Even more exciting, we are searching for even heavier exotic states that are composed purely of bottom quarks. The bottom quark is also more poetically known as the beauty quark. There are 4 beauties in a Chinese tale called Qi Shi, Wang Zhaojun, Yang Yuhuan, and Diao Chan. Can they come together to form various 4 beauty quark states? With more experimental information, theorists will be able to build a complete model for the dozens of exotic hadrons discovered in the last 2 decades, and also to figure out what role interference plays in this channel. For example, have you noticed that the width of the first state changes dramatically in 2 scenarios? More data and more effort are needed to unravel these puzzles of nature, and this is coming.